Previously in the sections 4.1 to 4.3, we studied how different compounding frequency would affect our notation in interest rate, in discount factor, in discount rate. Now we apply what we studied from there to analyze the impact on annuities. As we often expect, the first case we study would be annuities immediate, meaning the payments are made at the end of each period. Okay, but before we start something new, I want to quickly recap what we already studied, meaning there's a relation between payment once a year and more frequent than that. So that we usually call the P3 interest rate, the nominal. So it's I upper P. This is a nominal interest rate. Itself has no use. It's only for quotation. So itself is only for quotation. So we hardly use it directly. So it's you can think this as somehow a notation. The only place we somehow use it is to get the effective interest rate per period. So that is so this is now our new unit period. Okay, in all previous chapters, we set P to be 1, so 1 over P is just the 1 year. So we always deal with I upper P is the same as I, right? And the effective interest rate is given by IP divided by P. So that means if you put $1 at time 0, so $1 at 0 will grow to 1 plus IP divided by P at T equals 1 over P. So that is all we need to know from the nominal interest rate. Nominal interest rate is supposed to give us the effective interest rate per unit period. It's no longer per year, okay? And of course, if you want to convert it into 1 year, we need to compound this guy P times, right? Because if I draw it, here is 0, here's 1, here is 1 over P, here is 2 over P, here is 3 over P, all the way to P over P. So I need to do, I make my first deposit at time 0. It goes on for 1 over P period of time. Then I take it out, deposit again for another 1 over P period of time, then continue until the last one I get here. So on the left-hand side, if I do this, I raise the power to P times because we are in the world of compounding. And this is supposed to be my final value at time 1. So if there is an annual effective interest rate, well, then I should have this equality. Is the annual effective interest rate. So I use IR, so it's the interest rate. Okay, and this is the relation between nominal interest rate and the annual interest rate. So both are quoted for per year basis. So for the I, you can directly use it because this is the effective version. So if you make money, if you deposit money at time 0 and you want to take it out in 2 years, it's simply 1 plus I to the second, right? So you directly use it, but you cannot use it the same way when you have the nominal interest rate. You have to convert it to the effective interest rate per unit period and then count over 2 years how many unit periods you have, right? Because there are P periods over 1 year. So over 2 years, you're going to have 2 times P number of periods, okay? That's the most important information we need in order to learn the pricing of Annuity Immediate today. So now what we have is we have payments like this. So let me first type what we are trying to study now. It's now what we have things different. Okay, so we consider payments at the end of at the rate of $1 per year that are payable P3 for n years at the end of each period. So this is the annuity immediate we have. It is annuity immediate because all the payments are made at the end of each period. But contrasting to what we already knew, now each period is not 1 year. Right? Previously, everything's just 1 year. So if you have a $1 per year that payable, so because P is 1, so it's paid once a year, right? Then it's just a $1 at the end of each year. But now it's different, right? So now what we have is, so as usual, I always draw this timeline. So I will receive some payments over the over the period of n years, right? So I have n years. I know in each year I will receive a total of $1, okay, and without any discounting. So it's the nominal amount is $1, and it's payable piecely, which means I will receive P payments each year at the end of each period. So I'm supposed to right? I'm supposed to divide 1 year into P periods. This is T time. So this is the first period, this is the second, this is the third, this is the fourth, etc. Right? Of course, P can be less than 4. Right? Then let's say P is 2, then I have 1 over P, then 2 over P would be 1. Right? So basically, what I'm trying to illustrate is I will divide each year into P periods. Okay, and at the end of each period, I will receive 1 over P. That is fixed. I know the amount of payment is 1 over P. That is because the rate of payment is $1 per year, and I'm going to equally distribute it over P periods, meaning at the end of each period, I will receive 1 over P dollars. That is in the first year. And then I continue the same thing. So what we have, so it's very easy to see. We have so for this annuity, I will receive NP number of payments of equal size. Each payment is of size 1 over P dollars. I think that analysis is very clear, right? It's obvious. Now the thing is, we are trying to find the present value. So let the present value of this annuity immediate, okay, be denoted by this new notation. So we introduce the similar notation here. We have a superscript, round bracket, and put P. And what do we? Well, sometimes you can write the interest rate if you want, but it's often that people don't write. You put a specific number for a specific question. But we know this is the new notation we're going to use. It looks very close to what we used to denote, except now we put a new superscript, right? P down there. So this is called the piecely Annuity Immediate. I already wrote, so I don't need to write it again. So if you want to read this, it's called A upper P angle N. So what's extra is upper P, right? Previously, we have A angle N. That is the present value of this annuity. So obviously, this is the value at time 0, right? So it will be at this point. So now let's do the analysis, right? So what I usually do is to I have already done my first step is to draw a timeline, and I label the time, I label the payments to help me understand the payment series, right? And in the second step, what I do is I write the complete series. So for instance, this is my first payment. The amount is 1 over P. So I will need to discount by 1 over P period of time, right? And moving on to the second one, the amount is still 1 over P, but now the discounting will be for 2 over P periods, because for this, I will need to go back to 0. So the period of time is 2 over P. Okay, continue. 1 over P times the next one is 3 over P, right? So you can already see the pattern, right? 1 over P, 2 over P, 3 over P, 4 over P, etc. The amount in front is the same. And finally here, I will receive my last payment of size 1 over P, and I need to discount NP divided by P. So I know it's N years, right? Making sense because the last payment is made at time N. So that's N years after time 0. So I need to discount by N years. But of course, this is the case. So what can you see? This is nothing but a geometric series. It's a geometric, right? I can factor out 1 over P if I want. So let's say we factor out this. Then it's a geometric series with ratio. This is the common ratio, right? So it's 1 minus the common ratio. That's our denominator. For the numerator, it will be the first term, which is this guy, times 1 minus the ratio raised to the power of numbers, right? How many terms you have. We have from 1 to NP. We have NP terms, right? So that's from the summation of geometric series. That's why so far, I have already mentioned multiple times that the only formula we actually need is the sum of geometric series. Everything else is pretty much based on this simple result. You are supposed to know it from high school, actually. So then it's to do the rest of the work of simplifying everything, because here we do have, or let me do a little bit extra scratch work. So what is V? V is the 1 year discount factor. So it will be 1 divided by 1 plus I. Here, this I must be the effective, right? Must be the effective annual rate. Okay, in this context, we will need to convert it back to the nominal, right? Because that's what we are given. We are given this nominal rate I upper P instead of I directly. But of course, if you know I, that helps, right? So from here, what we can do is we can simplify a little. We can simplify because we know 1 over P we can keep. There's nothing we need to do. We can write V as 1 plus I. We can write to -1 because it saves some of the writing. Then, so it goes to the denominator. So NP divided by P is obviously N. So that's what we have on top. In the bottom, see what we have. So we will have 1 plus I, because I move this guy to the denominator. Okay, then I will have 1 minus v to the p's. I think we can keep it so far because, or we can write it, it doesn't matter. This is negative 1 over p, right? So do one more simplification. On top, there's nothing I need to do. At the bottom, let's distribute. So I get this is 1 over p. And then 1, right? Because this time this gives me 1. So that's pretty much all I need. I only used this condition. You may further simplify because if you look at this denominator, what is this? Let's go back here. So this is the general relation, right? I can take a fraction power of 1 over p on both sides, and then I minus 1 to the right-hand side. That's exactly what we have done here, right? Meaning I can write it as this will be I upper p divided by p. Okay, this will cancel this. So I have the first result. So let me put it in a nice box. This will be 1 minus v to the nth divided by I angle p. So this result comes from the geometric series, right? So that's what I derived. So let me put it here because we have several different variant to talk about. So it's not finished. So we will keep writing, okay, later on. So that is the pretty much the underlying mathematical analysis, right? So we haven't used any known result yet from annuity. So this is the basic analysis of payments and the basic analysis of discounting. After that, we apply a result from a geometric series to get the summation, and we simplify to get the final result. Okay. So far, we haven't used the relation between this and the standard annuity. So next, we do a little comparison to see what's going on with this new special annuity due, right? Before, we have only handled the payments for each year, right? The one payment for each year is either at the beginning or at the end. That's okay. That doesn't matter. But we have never dealt with multiple payments in a year. But time is a relative concept, right? You can well name 1 over p as 1. So let me get a different color. So time is a relative concept. Before, we always treat year as the unit. So 1 here refers to 1 year, 2 here refers to the end of 2 years, etc. So the default unit is year. But that does not have to be the case, right? I can use 1 month as 1, right? Then 1 year would have 12 months, right? And here what I do, I pick 1 over p. So I can well choose 1 over p as 1, meaning I take 1 over p as my current unit period. Then 1 year would become NP. 2 becomes, with that in mind, I give you an alternative. Up until the last one would be NP. So now in this, somehow the pink graph, unit period equals 1 over p. Okay, in the standard graph here in black, the unit period is 1 year. So let me erase this. Right, in this black graph, unit period is 1 year. So 1 refers to 1 year. But in this new graph, 1 year refers to not 1 year. 1 refers to 1 over p amount of time. Right. So I changed the time unit. Then this is a standard level annuity, right? So this is a level annuity. So for this, it would be, so from this easy way, I know they are NP payments of amount 1 over P, and the unit interest rate with I upper P divided by P. So that is the interest rate for each period, right? And then we go back to what we already know, right? We already discussed, denoted everything we wanted to know in the standard annuity. So I have an immediate result from this analysis. I will write it down directly, and we will go from there. So let me write it down first, and I will then explain what's going on, right? So let me still put the payment here. 1 over P, 1 over P. So as you can see from here, I use the standard notation of annuity immediate. But now instead of having n payments, I would have n times p payments. That explains this part, right? So now, because this refers to the number of payments, right? Previously, it would be the number of years. That's because there's only one payment in 1 year. So the number of payments equals the number of years. Here, it would be the number of periods, right? In our case, the number of periods equals the number of payments, NP. And then the second argument would be the effective interest rate per period, right? So remember, in this standard notation, N is the number of payments or number of years, because in that case, year is the unit period, and I is the effective interest rate per year, right? In that case, year is the unit period, okay? So that's why now everything makes sense in this new notation, right? I have NP number of payments. And for each period, the effective interest rate is I upper P divided by P. So that's why I have this new notation. But of course, I will need to times by the number, the size of the payment, because it's not one, it's actually 1 over P. So I just need to times by this. And obviously, you can use your previous knowledge to derive this. I mean, this is exactly what I have done here, right? That's the formula if you apply. But from the notation point of view, you can, of course, you can write the formula in this sense. So let me complete this box, right? So pretty much we have different notations for this A upper P angle N, right? The first formula directly comes from the mathematical derivation where I applied the result from geometric series. The second one is based on my analysis of the payments and my previous knowledge on a standard level annuity immediate, right? Both would work, both would lead to the same result. Once we studied the present value, of course, the next one would be the accumulated value, right? So let's write down the accumulated value. Accumulated value. So obviously it would be at time n, because that is the end of this special annuity. Everything's still the same. We would want to use S because it's accumulated value. We still put upper P to distinguish everything. So we know the distance between present value and accumulated value is n years. So all you need to do is to accumulate for n years. Okay. So if you pick what we have in the box, we just need to times by 1 plus I to the nth. So we will get 1 plus I to the nth minus 1 divided by I. So now I really don't encourage you to memorize any of the formulas, but in case you really want to do, right? You think if you look at this, everything looks pretty much the same as what we used to have, except this guy, right? Remember previously, it's if for a standard annuity immediate, you divide by I. For annuity due, you divide by D. If you have a continuously payable, you divide by delta. Now we are in the world of piecely payment, so you divide by IP. You see, it's in that sense. Once you know the standard one, the rest is the same, right? For the future value, is the same, right? You always have 1 plus I to the nth minus 1, right? And then it boils down to what would be your denominator. It can be I, it can be D, it can be delta. Now in the world of piecely payment, you divide by I angle P. So that's, of course, that is not a rigorous statement, but it might help you in case you really want to memorize any formula. I always against that. That is because you are allowed to use a financial calculator that has a built-in formula for the annuity immediate. And from here, right, I mean, there's really nothing you need to memorize as long as you know how to convert it to standard annuity, right? NP would be the new N. I angle P divided by P would be the new interest rate. So literally, there's no formula you need to memorize, right? Because the formula for this is built in. It's built into your financial calculator. And I wouldn't necessarily say analyzing this is complicated, right? You just need to draw the timeline to label all the payments and convert what you already know in this new context. And then everything will be done by your calculator. You just need to get a new for the number of payments, right? So now the number of payments, N would be NP, small n times P, right? And your I over Y would be IP divided by P. Remember, it's enlarged by 100 times. So if it's 1%, you type 1 instead of 1%, right? And then it's obvious, right? So if you want to save time, you can even put payment to be 1 over P. But of course, you can always times by 1 over P in the end once you know the annuity. So it's analysis first and then calculator. Then you save the labor work of memorizing formulas. Okay, I will end here for the theoretical part. In the next video, I will continue to solve the examples in the textbook.